Hello and welcome to this lecture on advanced electric drives. In the last lecture, we are discussing about the trapezoidally excited permanent magnet brushless DC motor drive. In trapezoidally excited motor, the back EMF is a trapezoidal waveform. Let us see an example of a trapezoidal motor. So, this is the view of a trapezoidal motor, and here we have 3-phase distributed windings, and the windings are phase A, phase B and phase C. The windings phase A, phase B and phase C are positioned in the space 120 degree apart. Phase B is shifted from phase A by 120 and phase C is shifted from phase B by 120, and these are distributed windings. It means the windings are placed in the slots. So, we have the slots, and each winding, if we see the phase A is spread over 60 degree here, and this is A prime, the return path of phase A. So, if A conductor carries dot current means it is coming out of the plane, and A prime will carry the cross current, something like this. We have a winding, we have a turn of a winding, and these two sides of the turn are placed 180 degree apart. So, if it is one turn of winding A, now this will be lying under A and this will be lying under A prime. So, if A is carrying a current like this, which is upward coming out of the plane, A prime will be carrying current which is downward. So, we can say this is the dot current and this one is the cross current. That is what is shown in A and A prime. Similarly, we have B and B prime, this is B, and then we have B prime, and B and B prime are the two sides of the windings. One side is A, other side is B prime. They are shifted by one pole pitch, that is 180 degree electrical angle, and if one of them is carrying dot current, the other one will carry the return current, that is the cross current. Similarly, we have phase C. Phase C is shifted from phase B by 120, and phase C has got C and C prime. C is for the one side of the turn and C prime is for the other side. So, this is how the windings are distributed. They are not concentric, they are in fact distributed in space. The distributed harmonics, distributed windings have one advantage, that the space harmonics are reduced. When we distribute the windings in the space, the space harmonics of the MMF are very much reduced, because they can be approximated to a trapezoidal waveform, and the harmonics are less compared to a concentric winding. Now, here the windings are distributed. So, if we see that phase A and A prime, each one is occupying 60 degree. So, here this is also 60 degree here, mechanical as well as electrical, because here we have assumed that the number of poles in this case is equal to 2. It is a 2-pole structure. We have one north pole and one south pole. Where is the north pole? Here we have a north pole of the rotor. The rotor is a permanent magnet and has got two poles. One is the north pole, other is the south pole, and the south pole is here. And this magnet, this permanent magnet are placed in the rotor. It looks like it is a surface mount permanent magnet rotor. The permanent magnet is housed in the surface. So, this is the permanent magnet for the north pole, and similarly this is a permanent magnet for the south pole. So, these magnets are placed in such a way that this side is north and this side is south, and the flux coming out of this permanent magnet are almost constant. So, in fact, if we plot the flux lines will be almost like a square wave. So, if we plot the flux lines of this magnet against theta r, here we have theta r in the x axis and flux density or B is in the y axis. So, we will see that flux density here is nearly constant. This for the north pole, and for the south pole something like this. So, this is 180 degree and this one is 360 degree. So, this is the flux density waveform of this kind of motor, where the rotor is a permanent magnet having two pole structure. Now, if we see here in the stator phase A, the phase A is spread over 60 degree here. So, when the permanent magnet is north pole is entering the stator phase A, gradually the south pole is going away, north pole is entering. So, there is a gradual rise of the induced EMF, because induced EMF we know by definition is BLV, flux density, L the length of the conductor into the linear velocity. So, when it is changing from north pole to south pole, gradually it takes some time to become fully south pole, or from north pole to south pole this will take some time, and this overlap time is 60 degree. It means for 60 degree interval a phase will have both north pole and south pole. So, during that time the induced EMF will be gradually rising. After the end of 60 degree the induced EMF will be constant. So, here if we plot the induced EMF of a phase, let us say that this is phase A, EA, and we are plotting this induced EMF in this case against theta r. So, this induced EMF will be a function of speed. So, this will be gradually rising in this case, and at the end of 60 degree interval it will be from fully north pole to fully south pole. Now, the present situation is the induced EMF in phase A, the phase A in this case is seeing full south pole, A prime is seeing full north pole. So, the south pole has fully entered under phase A. So, it means the induced EMF is maximum there, and this induced EMF is going to stay there for how much duration? This will be staying for another 120 degree. So, in that case what we will see here, that up to this time it will stay for 120 degree here. So, this is 60 degree and this is 120 and this is 180 degree. And after the end of a span of 120, the flux will again, the winding will again see the north pole. So, the south pole will be going away and the north pole will be entering, and again that will be duration of 60 degree. So, here it will again come back here and this is again 60 degree interval. So, this is 240 here, 180 plus 60 is 240, and this is going to stay for again another 120, and 240 plus 120 is 360 degree, and 360 is a complete of one cycle. So, we see that the induced EMF has completed one cycle. At the end of it, the same thing will repeat, the induced EMF will again rise and will be maximum here, and the same period will repeat. So, this is basically one cycle of induced EMF. It rises from negative maximum to positive maximum for 60 degree interval. It stays at the maximum value for a duration of 120 degree. Again, it reverses from positive maximum to negative maximum within a duration of 60 degree. It stays at the negative maximum here again for 120 degree. And this is the nature of the induced EMF in a single phase, that is in phase A. So, if it is an induced EMF in phase A, phase B, phase C are symmetrical. So, whatever is happening to phase A, the same thing will be happening to phase B and phase C respectively, but after a delay of 120 degree. It means phase B induced EMF will be shifted from phase A by 120. So, we can plot the complete induced EMF in the following fashion. So, we have a structure like this. So, we are plotting the induced EMF of each individual phases, phase A, phase B and phase C. These are the 60 degree intervals. So, we will start with phase A. For phase A, the induced EMF will be maximum here. Let us say we are talking about phase A, and then it will take about 60 degree for reversing it voltage amplitude. Then this will be stay with the negative maximum. Again, it will reverse the voltage to the positive value, and then it will stay here. So, this is for phase A, induced EMF in phase A, and this is origin. And what we are plotting? We are plotting against theta r, and theta r is nothing but omega r into t. Omega r is the rotor electrical speed, theta r is the rotor electrical angle. So, we are plotting the induced EMF against the rotor electrical angle. For a two pole structure, the electrical angle is same as the mechanical angle. So, theta r is the same mechanical angle of the rotor. So, in that case, this is the induced EMF seen in phase A. And for phase B, the phase B is shifted from phase A by 120. So, this is 60 degree interval. So, we can say 60, 120, and this is 180, and this is 240, 300, and this is 360, completion of one cycle. So, phase B will have this positive voltage after 120 degree of phase A, and this will display the same waveform like this. This is for phase B. So, this is EB here, the induced EMF of phase B of the trapezoidally excited motor, And what about phase C? Phase C will be shifted from phase B by again 120. So, phase C will have the maximum positive voltage here, and then this will have the negative voltage here for 120 degree, and again the maximum positive voltage here. So, this is the waveform for phase C. So, we are plotting everything against theta r, the rotor angle. So, and what we do here, how to control this kind of motor? We are having a trapezoidal excited permanent magnet motor, and we would like to control it. We would like to control it like a brushless DC motor. Now, here what we do, since the waveform, the back EMFs or the induced EMF of phase A, phase B and phase C are not sinusoidal, are in fact trapezoidal here, we excite the respective phases by quasi rectangular current waveform. So, the current of phase A looks like this. This is for phase A. We will say IA, similarly we will have IB, and similarly we have IC. So, let us say we can start with IA. And IA will be a quasi rectangular wave. If we extend this, we will be able to draw the current of phase A. So, this is what we want, that phase A current should be quasi rectangular. It should be something like this. It should have a value ID for some time, then 0, this minus ID, then 0, then again plus ID. Because what we want in this case is that EA and IA should be in phase. It means whenever the back EMF in this case is, in fact what we are doing here, we are having this current block like this. When the induced EMF is positive, the current is positive. When the induced EMF is negative, the current is also becoming negative. And as a result, the product of induced EMF and the current is always positive, and hence we have a positive power, and thus we have a positive torque. Similarly, for phase B, we can draw the current for phase B and phase C respectively. So, these are the 60 degree intervals that we have. And for phase B, we can have this IB will have this nature, positive here, then 0 here, and then negative here. Similarly, here we have 0 and we have negative. So, that in this case the current pulse essentially exists here. This is IB. When the back EMF is positive, we have the current positive. When the back EMF is negative, the current is becoming negative. Similarly, here also we have the negative current. As a result, in phase B also EA, EB and IB are in phase, and the product of EB and IB will be positive, and hence we have a positive power. Similarly, for phase C, we can have the current in the following fashion. This is the current, again a quasi rectangular current here. And here also we have 0 current, negative current. and this is IC, and we have the origin here, and these are all against theta r, the rotor angle. So, as the rotor rotates, the back EMF are trapezoidal in nature, and the current which has to be injected into the various phases will be of quasi rectangular in nature. How do we inject the currents? The currents are injected using a voltage source inverter. It is a 3-phase voltage source inverter which is used to inject the current into the 3 phases of the motor. So, we will see how the currents are injected by using a voltage source inverter. So, we have a voltage source inverter, a 3-phase voltage source inverter having the transistor switches, these are the diodes, anti-parallel diodes or the feedback diodes for feeding back inductive energy back to the source. Here we have the voltage here Vd, and this is the input current, that is Id. This for phase A. Similarly, for phase B, we have another leg for phase B. This for phase B of the inverter feeding the phase B of the motor, and then we have the C phase. So, these are the various transistors we have. Now, we can call this to be transistor T1, and correspondingly the diode, the feedback diode is D1, and this is T4, and the corresponding diode is D4. This is T3, and the diode is D3, and the transistor here is T6, and the diode here is D6. Here the transistor is T5, the diode is D5, the transistor is T2, and the diode is D2. So, we have 6 switches here, 6 transistor switches and 6 diodes, and the diodes are required to feed back the inductive power back to the source. And we have the 3 phases of the motor. The motor 3 phases are like this. We have phase A here, phase B, let us say phase C, maybe star connected. So, this is A, this is B, and this is C, and these are connected to the respective outputs of the inverter. And the current which is injected into the phase A is coming from phase A of this. So, this current is flowing here, this is called IA, or the phase A current that we have plotted in this case. And similarly, the current which is coming to phase B is actually coming from the inverter. This also IB, this is IB. For phase A it is IA, same current as this. Similarly, for phase C here is connected to this phase of the inverter, and this current is IC, same as this current here is IC. This is as per the convention. Now, let us say for the first 60-degree interval. So, when theta r in this case is greater than 0 and less than 60 degree, we are in the first sector, the first 60 degree. In the first 60 degree, the current IA is positive and current IB is negative, and the amplitude of this current are all ID. ID is the DC link current, which is assumed to be approximately constant. So, in this case, what we have here is this, that this current amplitude is ID. ID is constant, this is also ID, is the DC link current, this is ID, and this is also ID. So, this currents ID is basically coming from the DC link, that is this current. And here for the first 60 degree we can see that IA is positive, IA is plus ID, and what about IB? IB is minus ID. So, in the first 60 degree we see that IA is positive, but IB is negative. It means for the first 60 degree the transistor T1 is conducting. So, the current is flowing like this to IA to this particular phase, and it is returning through phase B like this and going to phase B and through the transistor T6. So, for this particular region 0 to 60 degree, we can say that T1 and T6 are operated, so that IA is positive and IB is negative. Now, the objective is that the current has to be confined to a band, so that the current becomes a rectangular nature. It is basically a quasi rectangular current waveform, but we cannot keep the DC link current absolutely constant. So, we have to control the current. How to control the current? The current can be controlled using hysteresis current control method. So, we can see how the current is controlled in the following way. We can control the current like this. This is the reference current, we can say it is ID star, and the actual current will be controlled within two bands here. Actual current will vary like this, going up and going down, going up and again going down. So, this actual current is essentially the current IA. So, we are controlling current IA. We are controlling current IA by controlling the switches, and the switches are T1 and T6. If you see the equivalent circuit, in the equivalent circuit we will see that we have two switches here. One switch is here and other switch is here, and we have a DC source which is present here, that is VD. We have T1 and we have T6, and this is connected to phase A, and we have phase B which is connected to this particular transistor. So, in this case when we turn on T1 and T6, the current flows in the following fashion. The current flows like this, it goes to phase A and returns back through phase B like this back to the source here. So, this is the direction, the path of the current in phase B and phase C. So, we can say here that IA is positive, IA is plus ID, this is our ID, and IB as per the convention is negative, it is flowing against the source. So, we can say that IB is minus ID. So, this ID will increase if we turn on T1 and T6. So, we can say that ID increases when T1 and T6 are turned on. And what about decreasing? This is the increasing current. So, we will say that for this region we are basically turning on T1 and T6. What about decreasing current? The current can be reduced when we turn off the switches. Now, when we turn off T1 and T6, what happens? When T1 and T6 are turned off, the load is basically an inductive load. In the inductive load, current will try to maintain its path. So, when the transistors are turned off, the current looks for an alternative path, and the alternative path is provided by the feedback diodes. The feedback diodes are here. So, we have the diodes in this case. The diodes are present here also. So, we have the diodes here, and this is the feedback diode for the other transistors which is not controlled here. So, this is D4, and we have another feedback diode which is present here, which is D3. So, when the transistors are turned off, the current direction should be maintained. So, we will maintain the current direction. So, this path is not there. So, the transistors are now off. So, the current has to be maintained. So, the current which was flowing in this direction, positive here and negative here, will look for an alternative path, and the alternative path is provided by the diodes. The diodes are, in this case, is D4. So, the current will come from D4, D4 turns on, and then this current will flow back through D3. So, in fact, when we turn off T1 and T6, automatically D3 and D4 will be turned on because of the nature of the current. And when these two diodes are turned on, a negative VD is applied across these two windings. Okay. So, we can see here that earlier this point was positive. Now, we see that when D4 is on, this terminal, the terminal of phase A, this is phase A terminal, and this is phase B terminal. Phase B was earlier positive because T1 was conducting. When D4 is conducting, A becomes negative. So, it means there is a tendency to reduce the current. Similarly, when T6 was conducting, the B terminal is connected to the negative of the DC voltage. When D3 is on now, the diode is on, B is connected to the positive of the DC voltage. So, in fact, when we switch off T1 and T6, D4 and D3 are automatically turned on, and they are on to reduce the current IA. So, ID increases when T1 and T6 are turned on. It means IA also increases. This is number 1, and we will say that ID decreases when T1 and T6 are turned off, which means if they are off, which means diodes D3 and D4 are on, and this also means IA decreases. So, for this region we have the conduction of D4 and D3, D3 and D4. So, we are able to control the current. The current can go high or increase, and current can also decrease, and this is done within two bands, and this band is called a hysteresis band. So, in fact, we have one band called upper hysteresis band and the other band called the lower hysteresis band. So, this is the upper band, and this is the lower band. So, if we control this current within two bands, we can keep the current approximately quasi-rectangular in nature. So, the current as a result would be something like this, is being controlled, and then after 120 degree duration it comes here and becomes 0, and then this is again controlled in the negative direction like this, and then it again goes to 0. So, this is the nature of IA, which can be approximated to approximately quasi rectangular waveform like this. Although we have the reference current which is a quasi rectangular, the actual current follows the reference within a hysteresis band. Now, let us try to find out the power in a brushless DC motor drive. In this case, we have a trapezoidally excited motor where the waveforms are trapezoidal, and the current in this case are quasi rectangular in nature, and the current exists when the voltage is positive. Now, let us try to calculate the power in such a drive. Now, here if you see the power in this case, P is because of the currents in all three phases. So, in fact, we can see that P is equal to EAIA plus EBIB plus ECIC. Now, if we take the 60 degree interval, the first 60 degree interval, that is this 60 degree interval, now we see that IA is positive and IB is negative and IC is 0. So, at any given time only two phases are conducting. So, for the first 60 degree we will see that IA is positive, and what about EA? EA is also positive. Let us assume that this EA value is capital E. The peak value is capital E here. Similarly, this is minus capital E, this is plus E, and this is symmetrical for all three phases. Now, the power in phase A is given as E into the current is ID. The current here is ID here, this current is ID. So, the power in phase A is E into ID. What about the power in phase B? The power in phase B, this is phase B, the voltage has reversed, this is minus E here, the current is also minus ID. So, we can say that the power here is minus E into minus ID. And what about phase C? In phase C the current is 0. So, we have current phase A is positive, phase B is negative, and phase C is 0. So, phase C does not contribute to any power for the first 60 degree. So, if we calculate power for the first 60 degree, it is EID plus minus E into minus ID, and that is equal to 2 ED, 2 EID. So, the power here is 2 E into ID. So, what about the torque? The torque is power by the mechanical speed, that is omega r m, and that is equal to 2 EID by omega r m, and we can say that is equal to, we have a torque constant, that is kT into ID. So, we can show that the torque is proportional to the DC link current. So, in fact, we can increase the torque by increasing the current and decrease the torque by decreasing the DC link current. So, the torque waveform will be a smooth waveform, that is a function of ID, and torque is equal to kT into ID, just like a DC machine. Now, let us see how we can control this motor with a closed loop control. So, we will see a closed loop control here. Closed loop speed control of a trapezoidally excited brushless DC motor drive. So, we have the expression here, T is equal to, torque is equal to kT into ID. So, in fact, we can control the torque by controlling current. So, if we want to have a closed loop speed control, we should be having a closed loop speed feedback. So, we have a reference speed, and then we compare the speed with the actual speed. So, we have the reference speed here, that is omega m star or omega r m star, the rotor mechanical speed, and that we compare with the actual speed of the rotor, that is omega r m, and we feed that to a PI controller. And then the output of this will give us the reference current or the reference torque, ID star, and this is a subtractor. We can subtract this ID from this, and we have a hysteresis control here, as we have discussed. So, this is hysteresis controller, and then the hysteresis controller will be giving the signal to a switching signal generator. So, we have a switching signal generator which will be generating the gate drives of the inverter that we have just discussed. So, this is the switching signal generator, and this will be generating the voltages, the signals SA for the phase A, the switching signal SB for phase B, and switching signal SC for the phase C. And then we have the inverter. The inverter is a voltage source inverter, So, this is a VSI, and here we have the DC link in this case, VD, and this feeds the BLDC motor, and then we have an encoder here, and the encoder gives the information about the rotor angle. The rotor angle is very important for synchronizing the power signal with the motor. So, we have the rotor angle which is generated or obtained from the encoder theta r, and this rotor angle information is fed to the switching signal generator. And then we have a speed calculator here. The information about theta r is fed to the speed calculator, which calculates the speed and we are closing the loop. So, this is output of the speed calculator is the speed, the rotor mechanical speed, which is used as a feedback for the closed loop speed control. Now, we know that we can also as well have braking operation. For the braking, we want to reduce the speed. So, the braking operation is identified by a negative speed error. Suppose the speed is now 1000 rpm. So, if the speed is 1000 rpm, if you want to brake the machine to 0 speed, this error will be negative, and accordingly we have to apply the signals in such a way that the torque will be negative. So, torque is given by K2 into ID, or if the phase sequence is reversed or the current signal is phase shifted by 180 degree, we can say this is for motoring region, for motoring, and for braking T is equal to minus KT into ID, the same DC link current, but we are going for braking. How do we go for the braking? For the braking, instead of applying positive current to the positive voltage, we will apply a negative current to a positive voltage. So, when the voltage is positive, we will make the corresponding phase current negative, that is possible. So, if we can do that, instead of having positive torque, we will have a negative torque, and torque will be given by minus of KT into ID. So, in fact, to have the braking operation, we will sense the sign of this error. So, this is the speed error, and we will be sensing the sign of this error. So, this is basically a sign block, and this is fed to the switching signal generator. So, this sign information will tell us whether the performance is or the choice is motoring or braking. So, if the error is positive, it is motoring. If the error is negative, it is a braking operation. For braking operation, the torque is negative. So, instead of applying a current which is in phase with the voltage like this, if this is the trapezoid, for motoring, what we do, we apply a positive phase current like this. This is for any given phase. So, IA and EA, suppose this is our voltage EA or induced EMF, this is the current, that is IA. For braking, we will have it different kind of waveforms. This is the voltage waveform here, and the current waveform is 180 degree phase shifted. So, this is the current for the braking operation. So, in this case, this could be EA and this is IA. So, this is for motoring, and this is the figure below this is a braking operation. and for braking we need to know the sign of this error, and this error is fed here to have a braking operation. So, this basically is a closed loop speed controlled brushless DC motor drive, where the motor is a trapezoidally excited motor, and this can be applied for applications, say for example automotive applications like electric scooters, electric vehicles also, and here we can have both forward motoring, also forward braking. Now, let us see how to model this brushless DC motor drive. Now, for the modeling we would like to have an idea of the back EMF. So, we will see the modeling aspect of brushless DC motor drive, and this modeling we will do dynamically. So, we will say that this is the dynamical modeling of BLDC motor. Now, we know that here we have 3 phases. So, the basic principle is that for any phase we have the applied voltage, and then we have the resistive drop, the rate of change of flux linkage, and the induced EMF. So, we can write down the equation for each phase. So, we will say that for phase A we will start with this, that the applied voltage A n is equal to R s I A n plus the induced EMF because of the inductances, that is L d by dt of I A, and we have the mutual between phase B and C, d by dt I B plus M d by dt I C plus the back EMF, that is E A. Similarly, we can write down the equation for phase B and phase C. So, these equations for phase A voltage, phase B voltage and phase C voltage equations are dynamical in nature, because they involve the derivative term, and the derivative terms are L d I A by dt, M d I B by dt and M d I C by dt. So, we can write down the equation for phase B and phase C, and then from that equation we can solve these equations to get an idea about the various currents, and the currents are I A, I B and I C. When we know the back EMFs and currents, we can find out the torque and hence the speed. The detailed modeling of this brushless DC motor drive will be discussed in the next lecture.